can understand. Now, let us look at a simple case. Instead of a rigid body, I'm going to take now a square plate. I'm going to take now a square plate or a rectangular plate. A rectangular plate, let us take. And this is of width B, depth D, and thickness P. So earlier what we were taking is a section we were taking, but now I am taking a plate, a rectangular plate of constant thickness T. Correct? This is straight line. Pardon, correct? So this is of constant thickness T. So now I have its since it is of uniform rigid body and I have bisymmetry its central axis. So this is my xg axis and this is my yg axis. That's known. So now if this plate is to rotate about xg axis, like this is the plate, this is the plate. If this plate is to rotate about xg axis is this. Yg axis means it is like that. If it is to rotate about an axis which is coming out of this, that is zg axis, then it is rotation like this. So now if this plate is to rotate about these three axes, what is the expression of mass moment of inertia is what I am going to explain you. So let us first find out Ixg. Ixg. So that to get, let me consider an elemental area, elemental volume. Because it's a mass, I'm going to consider an elemental volume. So this is elemental volume. At a distance of, this is y-axis, so it is at a distance y, and with the thickness dy. The thickness of the element is t. So now what is dA? So the dV volume is dA into t. What is dA? B into dy. B into dy into t is what is dV. Why dV? The mass of this element dm can be expressed as rho times dV. So it is B rho times T times dy. That is what is dm. So this is dm. So why do I require this dm? Is because the definition now Ixg is integration of this elemental mass moment of inertia about the xg axis. So that's going to be by definition it's at a distance y. So y square into dm. So if this elemental mass is rotating about xg axis and I integrate that from the limit minus d by 2 to d by 2 and I would get now my answer. So here y square into dm is rho times t times b times dy. So let me take rho is density of this material forming the rigid body, t is constant thickness of the plate, and b is again constant width. So if I take them out, I have rho t b is taken out and I have now integral y squared dy ranging from minus d by 2 to d by 2. So this is going to be rho times t times b into this integration. It is y cubed by 3 minus d by 2 to d by 2. I would have now rho tb. This is going to be d cubed by 8. So by 3 is so d cubed by 24. D cubed by 24 minus d cubed by minus of minus because it's cube, so minus of minus become plus 24. So I would get now rho T BD cube by 12. So what is BD cube by 12? It is rho times T times IXG area moment of inertia. So this BD cube by 12 is what is area of this rectangular section. It's moment of inertia, second moment of area about XG axis. Already we have done this. So that is what is equal to IXG mass moment of inertia. So the subscript I put so that we are able to look at now what is the relationship between area moment of inertia and mass moment of inertia. So if I know area moment of inertia of the section, if the section is extruded and forming the rigid body, then the inertia, rotation inertia about x-axis would be obtained just multiplying the section second moment of area by its density and its thickness. So this is what is important relationship. So if you know that, I would be able to get my expression of this mass moment of inertia. Before that, let us just to find out from this. So what am I going to do? I am going to write this expression again. What is this expression? Rho T BD cube by 12. I'm going to play around here. It is rho T into area. Area is what? B into D. So I'm taking BD out and here I have D square by 12. So now T into BD is what? BD is rectangular area, T is thickness. So this is going to be volume. Density into volume become mass. So M D squared by 12 is what is IXG mass. So mass moment of inertia of the plate is to rotate about, if this plate is to rotate about the XG axis like that, then that is given by the mass times D squared by 12. D squared by 12. That's what you are getting it, right? That is how you also get a relationship. So I know here BD cube by 12 multiplied by rho T, I get it. So I can use this relationship to find out even for other sections instead of doing integration. So for example, if I have to get now rotation of circular plate. Let me take circular plate. I'm not going to now integrate and find out. Rather, I'm going to use what is that you have understood. So now this is my XG axis. So now IXG mass of this circular plate. If this plate to rotate about XG, about its diameter like that, horizontal diameter, what is its mass moment of inertia? So that would be rho times T times into area moment of inertia about this. What is area moment of inertia? Pi r power 4 by 4, right? So now I can rewrite this as mass times the quantity. So that the quantity is what is equal to radius of gyration square, mk square. So we have seen that I is equal to mk square. So here if I have this expression on right hand side as mass times other quantity, that quantity is what is radius of gyration square, right? So now how do I write that? It is rho times the volume of this is T times pi r square, and r square I'm keeping by 4. So this quantity now is the mass of this circular plate into r squared by 4 is what is IXG mass. So the same, if I have my YG axis, if the circular plate is rotating about the vertical axis, vertical diameter, I would get IYG mass is same as this mr squared by 4. If I had to get the rotational inertia of the circular disk about the ZG axis, IZG, perpendicular axis theorem holds good here as well. IXG plus IYG. So that's going to be mr squared by 4 plus mr squared by 4. That's equal to mr squared by 2. So you should remember this. So if I have a circular disk, and the circular disk is rotating about its perpendicular axis, like appearing in this picture. And then inertia, rotation inertia is mr squared by 2. So this again you are able to derive from the relationship between mass moment of inertia and the area moment of inertia. Area, this, right? So same way here as well. For a rectangle also, what we have looked at, you can rewrite this formula. Like you have this md squared by 12. If you have to get Iyg mass, then it would be mb squared by 12. You can look at, derive that. If I have to get Izg, then it is Ixg plus Iyg, and that's going to be m into b squared plus d squared by 12. Is what is Izg. So what is the meaning of Izg? If I have my rectangular plate, this is my rectangular plate, its rotation is like this. If I have its rotation about its central axis rotating, then I would have the formula m into b squared plus d squared within bracket by 12. Right? So let us look at now, instead of a plate, if I have 1D, one dimensional bar, a slender bar. So I have a slender bar now. The slender bar is represented how? It is represented by means of an axis. Say this is x-axis. Here I have y-axis, and this is my z-axis. So I have the total length is now spread L by 2 on this side and L by 2 on this side. So this is my origin, and this distance is L by 2, and this distance is another L by 2. If that is so, now I have the 3 axes. So rotation about x-axis for one-dimensional figure, inertia is neglected. You don't feel that. If it is a slender bar, the rotation about its own axis is not where you don't require to consider its rotational inertia. Whereas the same bar is rotating about y-axis like this or an z-axis like this, you should consider rotational inertia. So for that, let us consider an elemental mass at a distance x from here. So at a distance x with thickness dx, let me consider an elemental length. And mass per m dash, let m dash is mass per unit length of this slender bar. If that is so, what is the mass of this element? Mass of the element dm would be m dash into the length of the element dx, m dash into dx. So if I have that, now I can find out what is my Iy. Means what? About this y-axis, what is its rotational inertia? To find out, Iy would be equal to integral x squared dm. So that's going to be integral x squared dm. It goes from x minus L by 2 to minus L by 2 to plus L by 2. So I can substitute dm here, that is m dash integral minus L by 2 to L by 2 and x squared dx. So that's going to be m dash into x cube by 3 minus L by 2 to L by 2. So substituting that here, m dash into L cube by 24 minus of minus L cube by 24. So that's going to be m dash into L cube by 12. So again, I want to write here mass times the quantity. So mass is m dash is mass per unit length into total length L. This L cube I split as L into L square by 12. So this quantity is total mass of the slender bar M L square into 12. So Iy of the slender bar, the rotation of the bar about y-axis is given by ml squared by 12. The same Iz also. Iz also is ml squared by 12, that is